Hi, my name is Manish Gupta, and in this video number 210, I am going to talk about ToolkenGPT, which is about augmenting frozen large language models with massive number of tools via tool embeddings. Okay, so let's get started and understand how does ToolkenGPT work. These days, it is very common to have large language models being augmented with tool usage, right? So essentially, we understand that large language models are awesome at generating coherent text, but they may not be great at doing certain things which are better done using tools. For example, a simple calculator, right? So there are two popular ways of integrating tool usage with large language models. One of them is fine tuning, the other is in context learning. In fine tuning, the idea is that you take a large language model and you take some tool usage data and you fine tune the large language model with some special tokens to represent the tool and help it understand how the tool works. So essentially, the large language model is not frozen because you have to sort of update the large language model, fine tune the model, and it cannot really handle large number of tools because you need label data for each of those models, each of those tools, right? It's not plug and play. It's not like, hey, you trained it for like 1,000 tools. Can you bring in, 1,001st tool at test time and will it work? It won't because you fine tuned it only for those limited number of 1,000 tools. Okay, but it can of course use extensive data, right? So that's that. The other way of helping large language models use tools is to basically do in context learning. So basically saying that your large language model is frozen and you basically define at test time what the tool does and therefore it's plug and play as well. But then, hey, it cannot really handle a massive tools, right? Tools that require large input data and large number of tools. Okay. So also it cannot really make use of any labeled data as such. So that's another problem. ToolkenGPT actually tries to combine these two methods and sort of comes up with a new method such that you have the large language model frozen, but at the same time, you actually have the original large language model is frozen, but you can augment more things to it. And you can handle massive tools and massive number of tools. And it's a plug and play. You can bring your new tool and make it work. And also it has the ability to use external data around tool usage. Okay. So how does ToolkenGPT work? The main idea behind ToolkenGPT is to represent each tool using a special token called as toolken. They call it special token as rather than token, they call it toolken, right? In that sense is a toolken, whatever you want to call it. Okay. And they learn an embedding for it. So the idea is that originally, if your vocabulary was V, you basically augment it with a new vocabulary tau, such that these tau contains one token for each of the tool that you want the model to learn, right? This enables tool calls in the same way as generating a regular word token. So essentially, to come up with the output, let's say the question was John has a rectangular garden of which the length is 64 meters and the width is 48 meters. He wants to divide the garden into identical square sections, each with the largest possible area. What's the area of each section? Now, um, you see, the model really wants to come with an output like that. The maximal side length of each section is GCD of 64, the greatest common divisor of 64 and 48, right? Now, how do you enable that? So GCD is a mathematical tool that the model wants to make use of. Um, and the way it can do is to basically call a special token, a toolken in that sense is called GCD, right? And that is how it enables tool calls in the same way as generating a regular word token. Okay. So the idea is that the model works in two modes, so a reasoning mode and a tool mode. So as soon as a toolken is predicted, the LLM, the model sort of temporarily switches to the special mode called the tool mode. And then what it does is it starts generating the arguments that are required at inference time. Of course, it generates the arguments that are required to be able to call the tool and therefore get the output. Now, once you get the output from the tool, those output representations are actually those outputs are taken back into the generation, and that's how the overall generation is obtained. Okay, so you see here, when you want to call GCD or when you want to call the square functions as to generate 256. So as soon as the square token is generated, it basically switches to the tool mode. And at train time, of course, you can give it demonstrations after the square tokens as to show how to generate things. But then at test time, what you want to do is to essentially pass 16 as an extra argument to it, such that the tool gets executed, the calculator gets executed. So the first step, is to do mode switch. Second step, actually call the tool, get the output to 56 and integrate the output into the typical stream of generation going back into the reasoning mode. Okay. So that's how this is done. Now, of course, to support this, what you want is not just embeddings for typical words, but you also want embeddings for various tools. So these are embeddings for each of those tools. For example, in mathematics case, it could be a square tool, GCT tool. There could be other kinds of tools for other capabilities, like for embodied reasoning, robots actually, grabbing, walking, sitting, all of those are tools. For knowledge base kind of tasks, knowledge graph tasks, you can have each relation as a tool like winner of, father of, and so on. Okay. So the idea is that while you're trying to train or fine tune this ToolkenGPT, you keep the original LLM parameters frozen, but you introduce a small number of additional training overhead in terms of toolken embedding. So you want to train those toolken embeddings nicely. Okay. So remember, this is different from prefix tuning, because in prefix tuning or some such similar methods, you don't just train the embeddings, but you actually train some small part of the large language model as well. Right? But here the large language model is majorly frozen. It's just that extra embedding tokens have to be trained for the new tools. Okay. Um, and in some ways, it is very similar to how infants learn a new tool through demonstrations from adults. So essentially, while training, you essentially don't just give, you know, so what you provide is basically a way of, of course, a new tool token, but the way the tool token embedding is trained is by giving several demonstrations as part of the samples, fine-tuning samples. Okay. So the fine tuning is done, of course, using the next word prediction loss, the typical loss. It's just that you also have weights associated with these toolken tokens rather than just the usual vocabulary word tokens. Okay. So fine tuning has to be done using some sort of parallel data where you essentially have the usual text, like the typical answer is the area is 256 square feet, and this is how it looks like when tokenized in words. But then you also have this tool called text. So you see, you have to basically train it to be able to call the tool with the toolken embedding plus the extra embeddings plus the extra tokens for passing the arguments. So for example, here you would basically call it here you would represent this text as the area is square and then any. So any sort of stands for these tokens. So this 2 is replaced by square and 5 and 6 by any. The remaining tokens are replaced by any such that they can be used so as to generate this final output. So the expectation is that the model is expected to generate S while it basically gets S dash as input. So the model should be able to understand that once it sees square, it has to basically go to square, call the tool called square with an appropriate number called as 16, so as to basically then generate output and then replace the stuff by 256 when in generating its final output. Okay. So therefore, the training data, the fine-tuning data is basically has pairs S dash, these kinds of pairs in the data set, and then you train or you fine-tune the model using this kind of a pairwise data such that you do not compute any loss over these any kind of tokens. But for everything else, you basically compute the loss in the usual way. Um, and and that is how you train this toolken GPT to be able to understand what are tool names and how to make use of them. Okay. So how does toolken GPT perform? Well, we will see how it performs in 3 different kinds of tasks: numerical reasoning tasks, knowledge-based question answering tasks, and embodied agents, embodied reasoning kind of tasks. So let's talk about the numeric reasoning or math tasks. So they experimented with 2 different data sets, GSM 8K and Func QA, right? Function QA. Okay. So this one basically makes use of 4 tools plus minus multiply and divide, but this one also makes use of totally 13 tools besides plus minus multiply and divide. It also has tools like absolute or these other tools uh, like you see square and GCD, LCM, and so on. Okay. So that's that. Now they compare with the three different methods, zero shot ChatGPT, which basically means you basically take the math problem and just ask ChatGPT, hey, tell me the solution, right? Or you can do chain of thought. You can basically, make it by just giving an extra prompt. Let's think step by step, right? Or you can basically do React, which basically means that so React basically stands for React Reasoning and Action, right? So basically here the action is done by the tool, so it also incorporates tool usage in that senses. But then it interleaves the verbal reasoning with tool usage. So there is a thinking reasoning step, which is verbal reasoning, and then there's a tool call step. So both of those steps. So in some ways, React baseline also uses tools. Okay. FunQA basically has two different kinds of subsets, one-hop questions and multi-hop questions. And what you observe is ToolkenGPT, of course, gives you way better results compared to all of those baselines. Now, another kind of data set with which they experiment with is based on knowledge-based question answering. So the idea is that you may want to ask who won the 2005-2006 FA Cup, and the answer is supposed to be Liverpool FC. Okay. So here the idea is that, well, this answer exists on Wikipedia. And what you could do is to consider each of those relationships, in this case, winner of relationship codified as P1346, right? You can treat each of these relationships as a tool. So each relation is basically a tool. To which the input argument is, of course, the subject entity, and what you want as output is basically the tail entity. So the knowledge base contains many fact triples, subject entity, relation, and tail entity. So you can consider that relation as the tool to which you pass the subject entity as input, and you get the tail entity as output. Okay. Now, again, they compare their ToolkenGPT with multiple other baselines, primarily these three baselines. The ToolkenGPT, again, there are two variants, the supervised variant and the synthetic data variant. In the supervised variant, what they do is for each of those relations, they sample 200 examples from their data set, and they basically do supervised learning using this loss, as we discussed in the previous slide. Okay. And then ToolkenGPT is synthetic. So what they do is to use the text description of each relation to synthesize training data with ChatGPT. They don't use the actual training data um, from the from the training data set, the labeled data set, but they basically generate synthetic data from GPT. Now remember, synthetic data is not really good quality. I mean, even though you may think that, hey, ChatGPT knows everything, it may not really be very, it can actually have its own hallucinations and so on, right? So that's that. Of course, they also compare. So the comparisons are here. You see the comparisons here. Let me first, in fact, just tell you about the plot. So on the y-axis, of course, accuracy. So the higher the better. On the x-axis is the number of tools. Okay. So what you see is that how many relations do you have? Do you basically want the model to be able to work with the questions around 30 relations versus up to 234 relations? So 234 tools. Okay. And remember, the larger the number of tools that you have, the more confusing it becomes for the model to be able to understand which tool to use to be able to answer this natural language question. Okay. However, what you observe is that ToolkenGPT, which is trained in a supervised manner, 200 examples for each of those 234 different tools, really does very well, right? Basically gives you 90% plus accuracy even with 234 different tools. Okay. Now, if you compare it with other baselines, and we'll talk about those baselines right here, prompting, ICL, and ICL description. So prompting is basically just the same as zero-shot ChatGPT. You essentially just give the question and ask it to answer based on its internal knowledge. You don't use any tool, no external knowledge used. Okay. ICL is basically, before asking the question, you list the tool demos and descriptions of all available tools. So you basically tell it in context learning. So you basically tell the ChatGPT model that, hey, uh, these are possible relations that you might want to care for, and you basically list down all of them because you don't know which one to list otherwise. Okay. And you also provide demos and descriptions of how to make use of those tools. Okay. Now, of course, here the prompt size is going to be pretty long, and no wonder it basically confuses the model, and the model really does not perform that well. So as you see, these are the baselines. So the green one is ICL, and the red one is ICL description. ICL description is a simpler form of ICL where before asking the question, you don't give both the demos and descriptions. You only give the description. You don't give the demos for ICL description. Okay. Okay. So clearly, supervised ToolkenGPT gives you way better results, even with 234 tools on this data set. Okay. Now, lastly, let me talk about embodied reasoning. So embodied reasoning basically means that so one of the popular data sets in this domain is virtual home. which is a simulation platform for typical household activities. You actually want the robot to do those activities. Okay. And therefore, what you want to generate are instructions for the robot to be able to do activities. In fact, here each sample looks like that. So each sample basically means that these three things are given to the model as input. One, a high level goal. For example, you want to tell the model read book. Okay. And then you also give it a detailed instruction. I would go lie down in my bed and open the book and start reading. That's the instructions. Okay. And then you also give a description of the environment. So the environment actually contains several objects, and there are actions that you can perform on those objects so as to satisfy the overall high level goal. That's basically the task. Right? So the description of environment could basically include the initial state of the agent and object list of the environment. For example, the agent could be in home office. So I'm in home office, and the objects again manipulate our mail, freezer, television, novel. It could be bed in this case or book in this case and so on. Okay. And what the model is expected to do is to output an executable plan, a sequence of steps, an ordered list of verb and object instructions. So given this object, what is the verb that you're going to, what is it that you're going to do with the object in the sequence is to obtain the final node, so as to achieve the overall task. Okay. In this case, there are 58 tools possible, all actions plus objects plus an end token just to denote that, hey, I'm done generating instructions for the tool to follow, for the tools to follow. Okay. Or for the robot to follow in this case. Okay, so what they do is, so here are the results, right? Here are the results that you see at the top. Of course, ToolkenGPT performs well across all metrics, but let's try to understand these metrics, right? And then there are three methods also to compare with. Okay, so grounding metric basically says that whatever that got generated basically had the right verbs associated with the right objects. For example, you don't say, lift bed. You can lie down on the bed. You can't lift bed, right? Or you don't say, read freezer, right? You can read a book, but you can't read a freezer and so on. So grounding basically means right verbs associated with the right objects. And the objects must be present in the environment. So if there's no book in the environment, you can't read a book in that sense, right? So that's that. So basically, as you see, ToolkenGPT achieves 100% score there. So it just doesn't generate, non-grounded or wrong kind of instructions which cannot be executed. Okay. Executable instructions are those that may be reasonable, but may not be you may not be able to execute them. Okay. Some of the instructions may be reasonable. They may be possible to be performed on an object, but hey, maybe, for example, if you have read the book already, you can't read it again, or maybe you can read it again. But the point is that you can do some actions, but in a particular order, right? So maybe the plan is generated, but it is not executable. Okay. So for example, asking the model to go left when there is a wall on the left and so on. Okay. Success basically denotes whether the task was done successfully or not. Success R is a relaxed version of success, which basically means that the task got done and then the model generated more instructions. So the final stage was reached somewhere in the plan, somewhere in the middle of the plan, not necessarily the end of the plan. Okay. And they compare with these three different methods. ICL is the simple in-context learning method where you prompt the LLM with all of these inputs, the action list, the three demo plans. You take three demo plans, and provide them as a way for the model to learn. And also, now, of course, these three demo plans are not going to capture all the 58 tools for sure. Okay. And you also give a new task with its goal description and environment description, a detailed description, environment description. Okay. So that's ICL. And as you observe, ICL does reasonably okay, 20% success, 30% relaxed success in that sense. So now, but ICL can actually produce things, right, and non-executable as well. And therefore, to help with groundedness, what you end up doing is translation, where you basically learn an LLM, or you train an LLM so as to basically generate admissible instructions that make sense. And this thing is basically done using sentence roberta large model using highest cosine similarity. So what you do is basically you try to generate an output from the large language model, and you choose those outputs which basically seem most promising using sentence roberta large model. Okay. Lastly, you can also do grounded decoding. What is grounded decoding? Well, that means that you use the large language model with all of those inputs and so on, but then the next token is generated using affordance grounded functions. What does that mean? That basically means that when you're trying to generate a verb for an object, you ensure that you generate it only from a vocabulary that is known. So basically, for example, for freezer, for things like television, you're going to only generate things like watch or see or things of that kind, rather than generating random other possible verbs associated with that. Similarly, the objects that you generate are going to be from a fixed list. So in some ways, it's basically constraint generation where you constrain the generated tokens to belong to either a verb or an object in the particular world. Okay. So what you observe is clearly that ToolkenGPT generates the best results compared to these three baselines. You also observe here's a case study for a task. So go to Office, sit at desk, turn on computer, enter password, open application, and begin work. Now, here, as you notice, the translation model actually generates sit at desk, while ToolkenGPT generates this sit at chair. Of course, sit at chair makes more sense than sit at desk, right? So this is the output generated by translation model, the translation baseline, which is not very good, but ToolkenGPT generates a very good output in that sense. Now, lastly, let me compare across these data sets, right? Let me compare how this, all of the experiments were actually performed using the Llama 7 billion, 7 billion parameter large language model, okay? So this is a comparison on QA, the functional QA, right? And on one hop and multi-hop, both of those kinds of data sets. And what you observe is that, of course, not just that ToolkenGPT gives you really good results compared to compared to other methods. Now, these are basically so yeah, it basically gives good results. But on the other hand, from a computing resource perspective, if you look at fine tuning, well, for fine tuning, you would have required 800 machines, each with 80 GB RAM. But ToolkenGPT, well, you just need to fine tune those embeddings. So therefore, what you need is basically just a 24 GB RAM machine and just one of those GPUs, right? 24 GB GPU RAM machine, right? And if you fine tune with LoRa fine tuning, you basically require like 40 minutes to LoRa fine tune, Llama 7 billion, so as to be able to get some good results. But ToolkenGPT basically gives you really good results in just 2 minutes. Okay, so there was already a comparison of these results here. Um, where ToolkenGPT can give you really, really nice results. But on the other hand, it basically just takes 2 minutes to basically fine tune this model compared to 40 minutes with fine tuning LoRa. So in summary, in this video, I talked about ToolkenGPT, which is a way of augmenting frozen large language models with massive external tools without any expensive fine tuning. It's a very, very cheap fine tuning. The secret sauce is to basically include a toolken embedding for each tool that you want to use. They show experiments on numerical reasoning, knowledge-based question answering, and embodied plan generation. And basically, the claim is that it can rapidly adapt and leverage new tools, although I don't think in the paper they showed experiments for new tools. But the idea is that, well, I mean, if you want to adapt to new tools, it's super simple. You essentially get a little more training data, whether synthetic or automated, and essentially use that to just fine tune a new embedding for the tool. So that's how you can actually sort of leverage new tools. Not zero shot, but yeah, and with minimal fine tuning required in that sense. Okay, so that's it for this video. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my search on my homepage. Thank you.